A very nice welcome to the quantum physics by Bhartiya quantum farmer Krisaks and Kishan. Now let's see again. In the previous lecture, we see the experimental proof of de Broglie equation, de Broglie hypothesis. Now let us consider an example. Electrons of 400 electron volt are diffracted through a crystal and a second order maxima is observed where the angle between the diffracted beam and incident beam is 30 degree. Now we have to calculate the wavelength of the electron matter wave that is lambda e, and the interplanar distance of those lattice plane which are responsible for this maxima, that is d. So from formula we have lambda e, that is electron wavelength, given by h by under root 2 m e, and using the given value, that is value of h and value of mass of electron and value of energy 400 volt means 400, and solving this we get the value of lambda e 0.61 into 10 to the power minus means 0.61 angstrom. Again we have lambda equals to 2d sine theta by n. So from this we get d equals to n lambda e by 2 sine theta, and using the given value, because this is second order diffraction, so n equals to 2, theta is equal to given 30 degree, and we earlier calculated electron wavelength matter wavelength lambda e equal to 0.61 angstrom. Using this value we get the spacing between the interplanar planes, interplanar distance between planes is 1.22 angstrom. Now we see, so after all along we have been accustomed to regarding an electron as a particle, and now it exhibits wave properties. These are clear from above equations. So what is the duality in an electron's behavior, and what is wave particle duality? Let us further explore the meaning of wave particle duality. To know this, first see the what do we mean by a particle. We define it as an entity possessing a definite position, mass, velocity, momentum, energy, etc. Its motion is described by Newton's law of motion. It must remain in a state of uniform motion or a state of rest when no external forces act on it. It should accelerate under the influence of a force field and move along a particular trajectory with a well-defined position and time relationship. Thus, in a nutshell, is a picture of a particle that we have acquired from our uh, study of classical physics so far. If there exists any entity which do not conform to this description of a particle, we should not call it a particle. Now, what do understand with a wave? So wave is characterized by its properties of velocity in a space, periodicity in a space, and periodicity in time. It possesses a wavelength, amplitude, frequency, and propagates at at certain wave velocity. It can transport energy without transport of matter. It cannot be localized and extends in a space. These are some basic ideas associated with a wave. If we find anything which does not conform to all of these ideas, we should not call it a wave. Having thus conceptualized a particle and a wave, then the the next step is fairly easy. If there exists something in nature which have neither purely particle properties, not purely wave properties, but has properties of wave, example mass, momentum, wavelength, amplitude, frequency, and is neither localized at a point nor extended to infinity, we should call it neither a particle nor a wave. For want of better name, we simply call it as a wave particle. In fact, that there are no particles and no waves in this universe, but only wave particle dualities should not unduly bother you. If that is the way nature works, that is the way it works. The definition of a wave and a particle are still very useful. To sum up, the concept of wave particle duality applies universally to all objects. However, since this duality involves Planck's constant, which has a very small value, the effect is applicable only in the macroscopic world. In the macroscopic world of our experience, object obey the classical law of classical law uh, of motion. Euferner also realized that wave particle duality arises uh, because of the finite value of Planck's constant. In classical physics, it is assumed that H equals to 0, that is, energy quanta do not exist. Hence, it cannot explain wave particle duality. However, by now, we have seen that there are compelling reasons to take energy in the quantized form such that each quanta of energy is equal to h nu or its integral multiple. One last word on the concept of wave particle duality. Its acceptance is not merely a question of belief or faith. It is a question of experimental observation and acceptance of a model for explaining them. So here we see the wave particle duality. Now let's summarize the lecture. So summary of lecture, we get the points like this. First, to explain black body radiation, Planck proposed the idea of quantum of energy for a harmonic oscillator. According to Planck's quantum postulate, quantum of energy capital E for a wave is given by cap E equals to h nu, where nu is the frequency of the wave and h is a universal constant known as Planck's constant. The idea was extended by Einstein to light to explain the photoelectric effect. Einstein regarded the quantum of light, the photon, to be a particle of energy E equals to h nu. Bohr used the quantum postulate and certain other postulates in his atomic model and successfully explained the stability of atom and the line spectra of hydrogen atom. He further gave the correspondence principle, which establishes a correspondence between classical and quantum physics. Just as the electromagnetic fields exhibit both wave-like and particle-like properties, de Broglie proposed that matter too so these properties, giving rise to wave particle duality. The de Broglie wavelength of a particle of momentum p is given by lambda equals to h by p. And for a free particle of mass m and energy E, lambda equals to h by under root 2 me. So these are the main points of the above lecture. Now see some questions from based on above lecture. First, derive Bohr's angular momentum quantization condition for the Bohr atom for de Broglie's relation. So here we know that. So let's derive this. To derive it, first see, de Broglie visualized that atomic electrons were confined waves and therefore produce a discrete stationary waves. Then only those orbits should be allowed in which an integral number of electron wavelengths could fit that circumference. For example, one wavelength would fit the circumference of the lowest atomic orbit and two or more electrons wavelength would fit into higher orbit. Thus, if the de Broglie waves of wavelength lambda fits a Bohr orbit of radius r, to satisfy the stationary condition, we must have 2 pi r equals to n lambda where n equals to 1, 2, 3 dash 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 dash. Since lambda equal to h by p equal to h by mv, we get 2 pi r 2 pi r mv by h equals to n, or mvr equals to n into h by 2 pi. So here we see the Bohr's angular momentum quantization condition. This is the angular momentum quantization condition, that is mvr. This represents angular momentum and equals to n into h by 2 pi. Next question is that calculate a high energy proton of 200 giga electron volt, 1 giga electron volt equal to 10 to the power 9 electron volt, are diffracted by a hydrogen target at an angle of theta. Theta given by the relation P sin theta equals to 1.2 divided by C into G electron volt. Note that the protons are moving at a relativistic energy. Estimate the radius of the proton. So let's solve this. We know that 1 giga electron volt equal to 10 to the power 9 electron volt. And if we consider the radius of proton is r, then we consider the dimension of the slit which scatters protons should be 2r. Now we have from diffraction rules, lambda equals to 2 into 2r sin theta, or sin theta is equal to lambda by 4r. This is equation 1. Now for proton given P equals to 200 giga electron volt by C, since E equal to Pc, hence sin theta equals to, it is also given in question, 1.2 giga electron volt by Pc equals to 1.2 by 200 equals to 0.06. The value of sin theta we have calculated. Again, we know that lambda equal to h pi v and equals to h by 200 giga electron volt by c, or equals to hc by 200 giga electron volt. Using all given value, we get the value calculated will come out to be, the lambda value of proton come out to be 6.212 into 10 to the power minus 18 meter. Hence, from equation 1, r equal to lambda by 4 sine theta. Now all value is known, so we, using these values, we can calculate the given value, and we get the value of r 2.5 into 10 to the power minus 16 meter. So this was the some calculations related to above problems. Again we see another examples. If there is another example, now we see the third question, which what is the third questions about. Let's see the third question, what tells about this. The third question is about the calculation of what is the third question? The third question is that a 150 electron volt increase in an electron's energy changes its de Broglie wavelength by a factor of 2. Calculate the initial de Broglie wavelength of the electron. So if we consider its solution, its solution is, since the energy of an electron increases, its wavelength will decrease. If lambda be the initial wavelength and E be the initial energy, and delta E be the increase in energy, we have lambda equals to h by this relation, and from question, after increase in energy, the lambda changed by a factor of 1 by 2. So lambda by 2 equals to h by this relation. And solving this, we see that we have a square both side. So lambda square by 4 equal to h square by 2m into 2me delta E equal to h square by, and using the value of 2me, h square by lambda square plus 2m delta E, and solving this finally like this, we found h square plus 2me delta E lambda square equal to 4h square, or 2m delta E lambda square equal to 3h square, or this implies lambda square equal to 3h square by 2m into delta E. Hence lambda equal to h open braces 3 by 2m delta E close braces to the power 1 by 2. This is the equation, and using all value, because all values are given, so h is 6.62 into 10 to the power minus 34 joule second, and another value is also given, that is 3 by 2 value is 1.5, and the mass of electron 9.1 into 10 to the power minus 31 kg. Energy is 150 volts, so this is the energy, and after calculating we get lambda equals to 1.73 angstrom. Answer. So initial wavelength of is 1.73 angstrom. Now next question. Calculate the de Broglie wavelength and the kinetic energy of electron which undergo first order Bragg diffraction by a nickel crystal at an angle of 30 degree. For nickel, D equals to 2.15 angstrom. So let's solve this. Here theta is given 30 degree and D equal to 2.15 angstrom. Now for first order Bragg's diffraction, that is n equals to 1, we get lambda equal to 2d sine theta, and using our given value 2 into 2.15 angstrom into sine 30 degree equals to 2.15 angstrom. Again, we know that E equals to h square by 2m into lambda square. So using all given value, we get the calculated value 32.5 electron volt, or in joule 52 into 10 to the power minus 90 joule. With this, I would like to end this chapter here.